Awesome. Okay. So the grade column is visible on Canvas. Canvas, I'm gonna leave it up. The cutoff between an A- and a B+ will be 90% or below. So if you're above a 90%, you'll have an A-, A, or A+. Similarly, the cutoff between a B- and a C+ will be 80% or below. I won't shift it up to 85. If a whole bunch of people get A's in here, cool. I'm on an objective standard, not trying to hit a particular percent of the class getting a certain grade. I understand that if you get a C- or below certain majors of SPIA, and I think it's just SPIA, but SPIA won't take you if you get a grade of C- or below in here. I don't give grades below C absent a serious lack of effort. Missing a major assignment. Some people are just work really hard at this and just don't perform very well in this course despite their hard work. They get to move through. Getting a C- or below in here generally involves some combination of not handing in the final or something like that, or handing in a problem set but only doing one of the questions, and just that sort of thing. So I haven't seen any worries of that in here yet, except for a few people who haven't dropped the course yet. And I can tell at this point who those people are. Okay, I just haven't heard from them in 3 weeks. So there's not much to worry about there. Some feedback from your comments. Thank you for those of you who submitted comments. What because it's the gist of it. More integration of statistical methods with R. At times the course feels like 2 different courses, one on R and one on stats concepts. That's coming. Before I could get you to a place where you're able to do statistics with R, I had to teach you R and teach you some statistics. You're going to find in the second half of the course, those two come together. The 3-day window for doing the graded P sets, because there's no time to really work my schedule around it. I can't do much about that 3-day window that was in the syllabus. That's just part of the course. There's going to be 3 of those assignments. They're going to be 3 days. In the past, I've done 5 or 7 days for that, and the assignments were longer. This time I shortened it to 3 days, just so that you know when it's coming and when you have to work. Teaching coding during lecture. I'll do a little bit of that moving forwards. Quite a few people talked about that. Having the handouts due the day before class, but wish you had a little bit more time to work on the handouts. We give you the handouts on day 1, and we do try to give you a chance to work on them at your own speed. In terms of doing them, in terms of what you hand into precept, you can always follow up with your preceptor after you hand it in to work with things. The preceptors in here have just been amazing, and I think they've been really great in helping to get you through this. Let's focus on papers and case studies in lecture and more in statistical concepts. That's actually going to happen in the second half of the course as well. When you do a statistical analysis, there's 2 big parts to it. What should I compare and how should I compare it? The first part of the course is on what should we compare? What are comparisons that are reasonable to make with what sort of data? The second is how, and that's what we'll talk about: p-values, regressions, confidence intervals, statistical significance, that sort of thing. I found that most of the mistakes that people make come in the what should we compare side, not the how should we compare it. R is actually going to do all of the statistical things for you. It'll give you a standard error, you can produce a confidence interval, it'll give you a p-value, but like R is going to do all that for you. Mathematically, it's just sort of like long division. Okay, it's just like tedious, and R does it. So the first part of this course is really getting you to think on about what you should compare, and then the second part starting today on how. More help with R, code and lectures, we'll do that a little bit. Longer precepts and more hands-on help with R. The this course used to be 80 minutes, then they were 50. Can you let me know in the end of the semester comments whether 80-minute precepts would be better? Just let me know at the end of the semester. Okay, we can go either way on that. And a main takeaway slide at the end of lecture, I'll start that up next lecture. Okay, any other comments on course feedback? But I'll try to incorporate as much of this as I can over the course of the next half of the semester. Any comments on the feedback or anything like that? I went through that quickly because I didn't want it to detract too much from the material. Today we're going to talk about loops. So, you know, loops are the peak of this course when it comes to R coding, okay? Many people struggle with loops. If you're in that category, that's okay. That's normal, that's expected. We're trying to get you over a learning curve. We teach you loops as the high point. It's the hardest thing we're going to do with coding this term, because looping opens up all sorts of doors for you that you can do with your own data down the line. That's the reason why we're doing it. It allows you to say, I don't want to do this one thing. I want to do this one thing a whole bunch of times to different subsets of my data. That's why we're focusing on it. It is very much the hardest part of this course. After loops, you'll find the R is going to be like, run a regression, and then there's a command in R that does it. Now do this, and there's a command in R that does it. We're going to shift, it's going to decrease quite a bit after this upcoming week or two. All right. Loops give you the ability to do really, really cool things. That's why we're teaching it. It's sort of a gateway to the point of data science type work. To give you an idea, the second problem set is going to involve a loop that's coming out next week. The second problem set in the past has involved going through voter file data, comparing, looking for the effects of voter ID laws in North Carolina on voter turnout, which took a loop, and it was difficult. We actually did it on an Amazon web server. Another year, we looked at conflict during the Arab Spring in order to see whether violent conflict was a leading or lagging indicator, whether violent protest was a leading or lagging indicator of violent conflict in the Mideast during the Arab Spring. Another one, we were using it to create maps that traced refugee flows as ISIS moved through Iraq in 2016, I believe. Where I'm going with this is and this one, I believe, I'm going to talk with the preceptors afterwards, but this one you're going to use a loop to look at patterns in compliance with patterns with compliance with stay-at-home orders under COVID. So I think we're going to take some Google data that has like literally where you are and look and see how many people move around when different mask mandates and stay-at-home mandates came out last year, and compare that with county level covariates or zip code level covariates. Now, hopefully that's very data sciencey, and I hope it sounds kind of cool. In order to do it, you need to know loops. You need to be able to take the data and perform the same operation a whole bunch of different times on different subsets of the data in slightly different ways, and then do these comparisons. What we're going to talk about today is looping through groups. This is going to be the basic loop that you're going to do. And we're going to talk about how to turn tapply into a loop. Now, to refresh, the command tapply, y comma x comma mean, is going to take a y variable, an x variable that's just a bunch of, it's going to treat as an index, and mean, it's going to apply the mean function to every value of x for y. So to give you an idea, just to start things off, y is going to be r norm 50, it's just 50 normal random variables, draws from a random normal. And x is just going to be the numbers 1 to 5 selected at random. So I have 5 groups, and I want to calculate the mean of y for each of those 5 groups. Tapply is one way to do it. A second way to do it is a loop. All right. So in order to turn tapply y, x mean into a loop, the first thing to do is put the loop in English. All right. Find the mean of y for every unique value of x. That's what we're trying to do. Be sure, if you're struggling with a loop, that you can carefully describe the operations that you're about to do in plain, straightforward English. It will help you conceptualize the work you're doing. The second part is you set the counter i.x to 1 and you get it to work for the first case. So you just get it to work for i.x equals 1. And then you put the code, then you put it in a for loop and you add a container if you need it. The struggle that many people have with loops is that you never write them in the order in which you finished, in the order in which they are finished. You write them from the inside out. And that's the mental sticking part that people have, because when you're coding, you're used to going like, do this, do this, do this, do this in this order. When you do a loop, you have to say, let's get it to work for the inner part of the loop, then let's embed it within a loop itself. So in order to do this, we're going to need the unique values of X. And that's what this line is going to give us. And this is going to give us the index that we're using. The second thing is we're going to need it to, we're going to set I.X to 1. And I.X is going to be the counter. We're going to set it to 1. We're going to get it to work for 1. Then we're going to loop it through 2, 3, 4, 5. Then what we want to do is mean.y is the mean of y for which X equals the first unique value. That's not our code. Don't actually type that in. That's sort of heuristic. But what we're going to do, and what you're going to do, is going to involve subsetting the data, doing things to it, saving it, and then subsetting the data differently, doing manipulations on it, and saving it and cycling through that process. So to do this, to subset, we can do the mean of y for which X equals, and what we want is the first unique value of X. And that's what that line is saying, because I.X is equal to 1, and unique.x is the vector of all unique values of X. That's just going to be 1, 2, 3, 4, 5. So here what we're doing is we're saying for a single iteration of the loop, we're just going to set the counter equal to 1, take the subset y to those observations for which X equals 1, and take the mean of those values. And that's what this line of code is telling us. Take the observations take the subset for which X equals the first unique value of X, take those Y's and take the average of them. The next step, and this is going to be the guts or the inner workings of the loop itself. The next step is we're going to embed this in a loop. So the lines we're adding now are in red. So in order to do this, we need a variable length.x, which is just the number of unique values of X. And we're going to add this for command. So this is saying for I.X and 1 to length.x, do this. To explain what this is doing, what this loop is about to do, what this code is about to do, is it's about to set I.X equal to 1. Then with I.X equals to 1, it's going to take the first unique value of X, the values of X that are equal to the first unique value of X, and the mean of the Y's for which X is equal to the first unique value of X. And that's what this line here is giving us. Then what the loop is going to do is it's going to increment I.X to 2. And it's going to say, now I'm going to set I.X to 2. I'm going to take the second unique value of X. I'm going to find the observations for which X is equal to its second unique value. I'm going to take the Y's for that value and then take the mean of that whole thing. Then it's going to increment I.X to 3, do the same process, I.X to 4, I.X to 5. In this case, it's going to stop at 5. Where's the structure used? You might go through a loop and perform this operation for every state in the union. You might perform it for every week in 2021 or 2020. You might perform it for every month. But the idea is we're going to take our data, split it up into these groups, and then using a loop, perform some operation on each group. That's the big idea that we're trying to be able to do. And I hope you can understand, at least from the description right now, the importance of this in a data science type sense of being able to handle large parts of data and do interesting things to all the little subsets of it. The last part is we have to turn mean.y into a container. Because what we've been doing is treating mean, in this line, we're treating mean.y as a scalar, just one value. So we're writing over it time and time again, which is not what we want to do. What we use is we use containers to save our operations on each subset. This is the only time. R is normally pretty good with new variables or new objects. For those who have done some other coding, the only time you have to declare a variable or its type in R in this course is right here. Okay, if you've done C++, I know you have to declare variables just up at the top, or anywhere really. But you have to declare variables and variable types. The only time you have to do this here is when this is a container. So what you're doing is you're saying, let's set up mean.y to be null, which just means it's something that I'm going to fill. Then what it'll do is R will automatically allow you to put something in the first position, the second position, the third position, the fourth position, the fifth position. The key takeaways from this discussion, aside from take the handout, work through it slowly, and you'll notice that the handout starts with the inner part, copy the code exactly until you understand it, then it embeds it in the same process that's up here. It embeds it within a for loop, it sets up a container, but it starts with that inner part first. Always start with the inner part and build out. Stick closely to what's on the handout, and we will stick closely in the problem set to what's on the handout. All right. Different variable names, different data sets, that sort of thing, but the structure of it will stick closely to what's on the handout. All right. Before we roll ahead, any questions on this? I don't expect this to be settled in everybody's heads, but any questions at the moment on this before you have a week to really dig into this and build on it? Okay. Okay, so today we're going to, this was sort of left from a couple of lectures ago. I just want to revisit it. In terms of the law of large numbers, the law of large numbers says that as we get more and more data, our answer gets closer and closer to the true value we're looking for. It justifies us getting more and more data. This discussion actually entails two parts, which is getting more data and getting more of the correct data. Okay, so this paper came out in the Proceedings for the National Academy of Sciences, which is a serious journal. And the idea, the title of it is that female hurricanes are deadlier than male hurricanes. The argument that the authors made, hurricanes in the United States, I don't know about is it worldwide? Are they named after males and females? I don't know about worldwide, but at least in the United States, hurricanes are named after a male and a female alternating gender of the name over the course of the hurricane season. Now, this paper argued that there was implicit sexism with how people reacted to hurricanes, where if a hurricane had a female name, they took it less seriously than a hurricane that had a male name. Now, play this one out in your head. And as you know, I do not shy away from talking about sexism, racism, all those sorts of issues in our society. This is one of those cases where a lot of people read it and went, not so sure. Imagine you live in Florida, there's a hurricane coming, and you say, oh my God, there's a hurricane coming. Hurricane George is coming. And then someone says, oh, no, it's Hurricane Jennifer. And you go, oh, phew. No. Always do those sorts of gut checks in these studies. They actually refer to the hurricanes in the paper as hurricanes and himicanes. Yeah, I know. But they argued that there was implicit sexism. Hurricanes with female names are not taken as seriously as those with male names. What I like about this paper is it's actually a testable hypothesis, right? It's up there with Groundhog's Day, Puxatawny Phil predicting more days, more winter. It doesn't quite, you hear it and you're like, I don't think that's quite true, but it's something that you can hold up to data, so we're obligated to hold it up to data. The question is, what kind of data do we use? So after reading the paper, some people went through it and they realized that the authors used the data from 1953 on, but names weren't randomized until 1979. From 1953 to 1978, all names were female. So what you have happening is from 1953 to 1978, global warming and the attendant increase in intensity of these sorts of extreme weather events hadn't really kicked in yet, nearly as much as since 1978. So there were a whole bunch of lower impact storms with fewer people dying. So there was no randomization at this point. What you were capturing is the fact that from 1953 to 1978, storms were both all named after females and less severe. Okay. So let's take the data from 1979 on. It turns out that to get this result, and if you do it from 1979 on, you actually do find a statistically significant result in the data. When you find these statistically significant results that seem odd, it's baked into the cake of our inference that some proportion of these will be false positives. Okay, this one just seemed particularly likely to be a false positive. So what you do is you say, if this effect actually exists in the world, where can we get more data from it, right? Like, let's test it again to make sure. And that should always be your impulse if possible. If you find a contrary or odd sounding effect, or people don't believe you, the best thing you can do is say, well, you know what? I'm gonna go gather this data over here and find the same effect. And if you find the same effect in two independent data sets in two different places, people really start to believe you, even if your results seem contrary to common sense or intuition. So in this case, if the authors went, some people went through, not the authors, some people went through and included tropical storms. The authors only looked at Atlantic hurricanes, then they included Pacific hurricanes as well. And then they also included foreign deaths because the hurricanes actually go through the Caribbean and touch Mexico on both sides. And the effect disappears. So the authors, the original authors of this paper, like, people read this and kind of rolled their eyes at it and went, oh gosh. But you dig into it, and I want to highlight that false positives exist. We'll talk about this in some detail from the next lecture on. There's nothing wrong with being honest and finding a false positive and reporting it. That's how science moves forwards. The idea is to make sure that if you have what might be a false positive, you go find more data to test it. And it's your job as part of a project to test your theories in several different places to confirm that it's not, you're not just reporting a false positive back. All right. Now, we need to define for just a moment the expected value of a random variable. The expected value of a random variable literally means what you'd expect if you were to draw one value of the random variable. It's a weighted average of all the values the variable could take, weighted by the density. So the expected value is a population parameter, not a statistic, which means we never see it. Okay. But if X can take on 5 different values, then its expected value is 1 times the probability of seeing 1, plus 2 times the probability of seeing 2, plus 3 times the probability of seeing 3, plus 4 times the probability of seeing 4, plus 5 times the probability of seeing 5. And that gives you this notation, this summation notation here. If we assume that X is continuous, then this summation just turns into an integral. But it's the same idea. Each value of X is weighted by the probability of seeing that value. And in this case, these probabilities sum to 1. And in this case, the integral of the density is 1. So we're not going to go too far into expectations. I just want to mark them as something you'll be encountering in future courses. But what I want you to understand from expectations is the law of large numbers. And the law of large numbers tells us that as we get more and more data, the sample mean approaches the population mean. It approaches the expected value. In fact, as we get more and more data, we expect the sample mean gets closer and closer to the true population mean, or by the population mean, I mean the true expectation. This is a reassuring result, which justifies getting more data. That's what it's for. It's the mathematical device that we use to justify going and getting those last 500 observations. You're going to get closer to the true value or closer to the correct value the more observations you have. And that's what the law of large numbers is going to give us. With more and more observations, we get closer to the expectation. Okay. The expectation deals with point estimation, which is just simply, what do I think this number actually, what do I think the mean of this number actually is? What do I think the expected value of this number actually is? We're going to shift for a moment, actually going to shift for a while and move from estimation to inference. So estimation says, here's my best estimate of this parameter that I want, the mean of a treated group in a clinical trial or something like that. Inference says, how close do I think that sample mean, my sample mean is to the true mean that I'm interested in. Another way to put it is, what's the uncertainty in my estimate? And that's what we're going to shift to next. Thinking about how to connect our estimate to the true value we're trying to estimate. Now, when we talk about connecting the estimate to the true value, we never actually know how close the estimate is to the true value because we don't know the true value. But we can connect them probabilistically. And that's the next step we're going to take. That's going to get us to the normal approximation and the central limit theorem. So in this particular case, we want to think about the sampling distribution of our estimator. The sampling distribution of our estimator is the distribution of the estimate over multiple runs of the experiment or multiple runs of the study. So let's think about this for a second. We observe a single sample and a single mean. What we want to know is that if we were to observe a different sample, we'd get a different mean. And every single sample we could observe would give us a different mean. And we want to characterize the distribution of those means across repeated samples. That's going to give us our estimate of uncertainty. Let's see. So the normal distribution appears through the sum of random binary outcomes. Let's see. I sort of feel like a video. Here we go. The quincunx, which is right here, it was actually invented by Sir Francis Galton, the fellow who did the regression, the standard deviation, and eugenics. Also was the first one to demonstrate the central limit theorem in this case. Skip ads. Oh, hold on, let me turn up this up. So Francis Galton was interested in proving how a set of random 0-1 decisions could appear to look like a bell curve. And he developed this machine here called the quincunx and presented it as a paper to the Royal Statistical Society back in the mid-19th century, proving one of the first demonstrations of the central limit theorem. So let's see what this looks like. And also this fellow's accent is worth the cost of admission. Does he sound mumbly to you, or can you hear him? What was that? Mumbly, or can you hear? Okay. Oh, okay. He has the most wonderful British, like I wish I had a British accent. Um, okay, let me share this 1 second. All right, so the idea behind the quincunx, which showed up in that video, is that if we could think of some political, social, or physical process as being the result of a set of 0-1 decisions, then we expect the result of an aggregate of those decisions to follow a normal distribution. That distribution that we were approximating was a normal, you saw the bell curve, right, on the bottom of the quincunx. If we can think of a process, if we can think of a process as just simply a sum of yes or no decisions, then it's approximately, a sum of those is approximately normal. And that right there is the basic insight of the central limit theorem. If there's a process that's a set of 0-1 decisions, then it's approximately normal. And this was the first central limit theorem. One example is polling. So what you'll see here are, I think this is from the 2012 election, I believe. But if you go through and you survey people, and you take a survey of people and you ask them, do you approve of the president, right? Or would you support the incumbent president over his challenge? Everyone in the room everyone who's asked that question, it's a 0-1 decision for them, right? Which means if we add them up and take an average, we expect it to be normally distributed. To put it differently, if we were to have a bunch of different polls from a single state, we'd expect the polls to appear approximately normally distributed. This is the distribution of polls for, I believe, the 2 weeks prior to the 2012 election, which was Obama-Romney. And a bunch of different pollsters were polling Colorado heavily because it was a swing state that cycle. And they wanted to know, what is the true outcome going to be, right? Or at least what's the true outcome as of today? All of the decisions in polling are 0-1. Do you approve or not? It's just averaged over a whole group of people. If you average those if you look at the distribution of polls from Colorado that cycle, they look like this, which is approximately normally distributed. It's not exactly normally distributed because there were only 15 or 20 values in there, but the normal approximation seems reasonable when we talk about polling, because the underlying data is generated from an average of 0-1 decisions. What this is going to allow us to do is actually construct a measure of uncertainty from a single poll. Because given a single poll, I know what the expected value, I know what my estimate is. And then I get my uncertainty estimate by assuming that the distribution is approximately normal. So I can calculate the mean and the standard error for my estimate and use those to approximate the underlying uncertainty in my estimate itself. What allows me to do that is the central limit theorem, which I give here. The original statement of the central limit theorem actually involved just coin flips or sums of binary variables. It actually holds for any data, for any variable. It can be continuous, it can be binary, it can be discrete. And it's been extended mathematically since Galton did it clearly. But the idea behind it is that as n gets large, the sample mean is distributed normally around the true mean with the variance of x over n. Another way to write this is that if we write this as a z statistic, x bar minus its population mean over its standard error down here is approximately normal, is approximately standard normal. Now, what this is going to allow us to do, and the power of the central limit theorem, is placing the sample average here and the population mean there in a single equation and connecting them through a normal distribution. So we have a single representation of the data that connects our sample mean to the true mean that we're interested in. So the question of inference is, how close is x bar to E of x as a function of its standard error down at the bottom? The denominator is the standard error. So let's go back. We were talking about what we do with loops. This was from the 2012 election. Yeah, Obama-Romney. In this election, what we did per state was we took all the polls 2 weeks before the election in each state in the 2012 presidential campaign. We took all the polls in the 2 weeks before the election. For each state, we calculated the mean and the standard deviation of the polls for that state. Then we drew another normal random variable with the same mean and standard deviation and pretended that was the outcome. All right. We did that for each state. So for every state, what we did was we created a new poll that we pretended was the actual election outcome, where the new poll was created from a normal generated around the existing polls. All right, so we were simulating a whole bunch of different election results. Then using a loop, we did that 10,000 times. And if you look at the data from that cycle, Obama won 332, Romney got 206. So in this case, what we can do is for each election that we ran, each pseudo election, each election that we simulated from the polling data, we could add up the electoral votes at the bottom and just see who won. This is the distribution of electoral votes for Obama and for Romney in that cycle. The percentage of the time that Obama won given our simulation was 97.3. The percentage of time that Romney won was 2.7. The actual results were 332 for Obama. Romney got 206, which if you look at it is this bump right here. So our estimate, we underestimated Obama. I think we had him getting closer to like 290. There was an extra state that he won that we didn't anticipate, but it was this bump right here that was the actual result. And then for each state, we could estimate how much it went for Obama or Romney across our simulations. And this was the US electoral map for 2012 that we predicted. All this was done before the election and we got it right. In 2016, we'll revisit. All right. Luckily, I was on sabbatical that semester. That's all I'm saying. So what we need to start thinking about, we've been focusing quite a bit on estimation in this course. I don't just want us to think about estimation, but to start thinking about uncertainty. Uncertainty is a measure of how precise we think our estimate is. We'll have multiple different conceptions of uncertainty before the semester's through, but that's just where we're going to start. Uncertainty we're going to use to calculate a margin of error. Okay? The uncertainty that we get in our estimator is referred to as the sampling distribution. So the sampling distribution of an estimate is across repeated samples, what is the distribution of that estimator? In this example here, the sampling distribution of electoral votes looks like this. It turns out to be kind of normal, but not exactly normal, because the electoral votes come in and out via close, right? Like you either win a state or not. So it adds a little bit of skewness to the statistic, but that's still reasonably normal looking, at least as a social scientist looking at it. So if we look at the estimate for Romney's electoral votes, this is our sampling distribution. Our estimate across repeated samples looks like this. The estimation error is how far our estimate is from the truth. And in many cases, we're going to want to minimize our estimation error. We want our estimate to be as close to the truth as possible. We can't make claims about the size of the estimation error in our sample because we don't know what theta naught, the true value, is. but by using the central limit theorem, we can connect them using a normal distribution. The bias of an estimator is the extent to which its expected value is above or below the true value that we're interested in. We talked about this earlier, but to the extent that we think that our estimator is systematically above or below what we're looking for, then it's biased. It's unbiased if we have no reason to suspect that it's systematically above or below the true value we're trying to estimate. The efficiency of its estimator is its variance. So in this case, efficiency is just going to measure the spread of our estimate, which is going to govern our estimate of the margin of error. The last part follows directly from the law of large numbers, which is that as we get more and more data, we expect our estimator to converge to the true value. Okay. Now, these are all distinct concepts that we're going to tie together in particular ways over the next few lectures. So I'm dropping these on you, but we're going to revisit them and piece them together. But just to talk them through for a moment, normally we're going to construct estimators that have the lowest possible estimation error and that are unbiased. That's what the central limit theorem is going to give us. The efficiency of the estimator is going to give us a margin of error. And consistency is going to guarantee that as we get more and more observations, we get closer and closer to the truth. Now, keeping with the, today's had a little bit of a data science-y feel to it, so we'll keep with this. The first breakthrough in modern computational data science was a statistical method called the bootstrap. Okay, it dates back to the late 70s. And the idea of the bootstrap is a data-driven way to estimate the variance of our estimate. Prior to the bootstrap and prior to computers, people would always estimate the variance of their estimator and get their margin of error by hand. And for those of you who haven't taken graduate level, PhD level mathematical statistics, oh my God, that can be tedious. So one of the advantages of the bootstraps came out in the late 70s, came of age in the 80s and 90s, is that it allowed us to calculate variances and to calculate the sampling distribution of our estimator by brute force with our computers. So it was a computational method to calculate margins of error that didn't rely on a normal approximation or anything like that. The idea behind the bootstrap, and I'll walk through the R code with this next lecture because we're running out of time today. The idea behind the bootstrap is we assume there's a population and we observe a sample. Now, what we want to know is the variance or the distribution of this sample. So what we're going to do is we're going to take our sample and we're going to treat it like our population. And we're going to draw bootstrap samples from this sample over and over and over again. And let me explain to you what a bootstrap sample is. Let's see. Yeah, I'll start here, then we'll work back to the example. We'll work back to the applied example in a moment. Let's say we observe X1, X2, X3, X4, and X5. Okay, these are measures of something from 5 different observations. We want to know how are we going to get a margin of error or an uncertainty estimate from these 5 data. The bootstrap samples are drawing 5 values from this with replacement. So in this case, the 5 bootstrap samples, the first one might be X5, X5, X3, X4, X4. So we're taking 5 values from 1 to 5 with replacement. And we're going to take the mean of this. Then we're going to take the second one, which was X4, X4, X2, X3, X1. The third one might be X4, X5, X4, X1, X2. The important part, though, is we're going to take the sample mean of this, but we're going to use these bootstrap samples to estimate the underlying uncertainty to get our margin of error estimates. Let me give you an example. Actually, We're going to walk through this with an example. We're stopping here. We're not stopping with the bootstrap. We'll resume the bootstrap in detail next lecture. So don't walk away thinking that's done and you need to like worry about that. We'll spend some time on that in the next lecture. Otherwise, this is just a good break point. I'll see you on Thursday.